Hello.
Hi, Tammy. Hi, Paul.
Hello. Uh,
How you, how you holding up, Christian?
Well, good. I am making it through. I am in the
I
slog of posters. Everybody's
oh
like printing their posters for E-Days and 498. I'm ready to be done reviewing posters. But, okay.
yeah, I bet. I'm gonna send you a photo because I think I'm making it worse.
do you hear any background noise from me?
No,
Okay.
you seem fine.
Okay. I am sitting in a hotel lobby and there is hotel lobby music.
You'll tell them to turn it up.
No, I'm going to leave my camera off if that's okay to preserve battery. I am plugged in charging, but it's a slow charge.
Cool. Yeah, that's fine. Danny, sorry I didn't get back to you. I barely had a class today. I was lucky to show up and look like I had something to say.
No worries at all.
I may not have sent out a reminder for this meeting. Did I totally forget? Dang it. I'm sorry, guys.
Okay, the calendar invite exists, so
I
a
know,
reminder
but
isn't necessary.
too busy working on the content to remind people to come, but at least you came. Thank you. Ellison said she wouldn't be here. I know Misa had an install this morning, but so I never know if he's going to be back. Um, so let's just wait a couple more minutes. Hello, everyone. Sorry for my failure to remind this week. We also have a meeting next week, just in case I forget again. So, uh, Paul, if you could mute yourself, that would be good. Awesome, thanks. Yeah, so as I didn't say in the reminder, um, Danny is going to talk about some work we've been doing with wind attribution, and I'll let him explain everything.
Okay, everybody, I'm here to explain everything.
I was gonna give a preface, but then I thought might steal your thunder.
No, it's fine here. So I will share this, and then I never know. Can I present in? What can I do?
Yeah, I think so. You should be able to, yeah,
Can
great.
everybody see the slide?
Yep, looks good.
Awesome. Okay, cool. So what I am going to be talking about today is some of our attempts to do flow attribution and Site 301. So there are some residents of Site 301 on this call, so feel free to chime in if I get anything wrong about the site. It's Tammy and Paul's house. Spoiler alert. So when we're doing site attribution, what we're trying to do is we're trying to figure out what mechanism is causing flow into or out of the home. So kind of what's driving those underlying pressure differences. So the mechanisms that will do this include mechanical ventilation. So This is, something is moving that air from one zone inside to outside or outside to inside, right? So this is something that we're doing, like a fan, range hood, something of that nature. Um, and I will also apologize in advance when I put these figures into the CSU format. The color palette went all catawampus, so some of these colors are egregious, and I decided not to change it as a small protest against their color palette. So this is mechanical ventilation. The next uh, the next mechanism is stack effect. So stack is driven by temperature. So we have one temperature inside and a different temperature outside. So in this case, we have warmer air inside than outside, and we will have flow in the bottom and then out the top. And you'll notice that the magnitude of that flow increases as you get closer to the roof line and as you get closer to the ground, right? Because that's where the biggest pressure differences are going to be. The last one is wind. So we have wind hits one side of a house, and we have an increase in pressure on that side. You get infiltration on that side of the house. And then you'll have negative pressure on the other side, and it will pull air out from that side. And then I see there's stuff in the chat. Thank you, Paul. Tammy made this one, so I can't take any credit for this. Okay, so this is kind of yeah, Tammy, you made it last summer in preparation for Healthy Buildings a long time ago. So this is kind of another figure showing that visualization of wind affecting a house. So this is from this slightly blurry picture is from the MIT Learning Lab. So we have positive pressure on one side. And then what I like about this picture is it shows kind of the swirling nature of the leeward side on the opposite side of the wind. Kind of you have negative suction, the air being pulled out, but it's very turbulent. It's all over the place. It's not that smooth air coming in from the other side. And so how we look at this and what we do for normal sites is we will put 3 manometers, so 3 differential pressure sensors. So 2 on as close to the roof line as we can get on opposite sides of the home, and then 1 as close to the floor as we can get on one side or another of the house. Kind of, we want to make sure that it's on the same side as those upper level measurements. So what we hope to do with these measurements and what we measure is vertically, so this blue one, we want to measure the pressure due to stack, and then green, kind of horizontally, we want to measure the pressure due to wind, right? So if we have wind coming in from one side, it'll show differential pressure from side to side. Excuse me, if we have pressure due to stack, you'll see a difference in pressure from top to bottom. That's kind of the idea. With 301, we did something a little bit different, and we doubled the number of manometers. So we have a high, a medium, and a low for both sides of the home. And so we can really look at that pressure gradient from top to bottom as well as from side to side. So a lot more instruments. And then you'll also notice my everyone's the little tiles of everyone's faces is blocking this, but we have the weather station on one side, and that's going to give us all of our meteorology data outside. And we want that to be as close to roof line as possible. We're not just putting it anywhere. We want to get it as high as we can. So, but that gives us a challenge, right? So given our instrumentation, how do we attribute pressure differences to different mechanisms, right? So we can start to look at some of these, looking from side to side, looking up and down. But what happens if you have multiple things happening at once? It kind of starts to, you start to get some influences from each in the other, and it starts to get complicated. It's not a very clear, straightforward process. So when we take pressure measurements and we start to turn them into flow, we put them into these different equations that tell us how much air is moving based on these pressure differences. So for these, they call them infiltration models. This is kind of the nitty gritty of it, and we'll get even nittier and grittier in a few slides. But kind of all equations have this this format. So we'll have the leakage area that tells us how big are the gaps and cracks? What is the area of those holes in the envelope of the building, in the walls and the windows? There's a geometric factor, so that tells us what is the spatial distribution of the leakage compared to the pressure. So where in the house are those leaks? And then the last term is those pressure measurements. So, what is the pressure difference between inside and outside? And that's kind of what's different with this, is that we have a lot finer resolution of pressure differences because we've put way more instruments in there. Tammy, anything you want to add about any of this?
Not yet,
Did I
you
miss
did
anything?
great.
Okay, cool. So kind of what are these models doing? Like what is inside the model themselves? So if we look at this general form of the model, we can start to break it down. So the A term, as I kind of mentioned, that's our leakage area. So we get that from doing a blower door. So when we do the blower door, it tells us what is the total area of leakage in that home. We also have the measured pressure. So that's the differential pressure. And then we have this flow exponent, N. And that kind of tells us the quality of what are those holes, those gaps and cracks like. Is it easy for air to pass through? Is it a little bit harder for air to pass through? And that will also be from the blower door as well. And then there's the K term and that geometric distribution term. And this is kind of the sticky, tricky one that is hard to deal with. So K is calculated from an understanding of where pressures are greatest compared to the estimates of where the leakage is. And kind of this figure on the left shows you it's kind of a visualization of where the leakage is in the home compared to the pressure differences. So you might have a situation where the pressure is greatest, there's no leaks, and so there's going to be no flow there. Or conversely, you might have an area where, right in the middle where there's no pressure difference, but maybe there's a big old hole there. So we won't have any flow through there because there's no pressure difference, right? And these equations on the bottom are kind of the nittier and the grittier that I mentioned of how do you get at the geometric distribution. And these are for stack effect. So you can see it's kind of a relationship between R, which is the fraction of leakage through the roof of the home, and X, which is the leakage of the fraction of roof versus floor, as well as this beta naught term, which is the neutral pressure level, kind of where it is where pressure is equal inside and outside. So kind of where there's going to be no flow in between. But determining that K factor, the geometric factor, is much harder for wind. So to try and get at that, when we have to try and answer these 4 questions. Paul, I see a hand.
Yeah, I believe that R is the fraction through the walls, not the roof.
Okay. Yes. Yeah. So the fraction of the leakage to the walls compared to through the roof.
No, as a fraction of the total leakage.
Of the total. Okay, got it. Okay. Yeah.
So if all of the leakage is showing is 1, then and when the assumption is that half of the leakage is in the walls and the other half is split evenly between the floor and the ceiling. So R would be 0.5 because half of the total is through the walls.
Yeah, got it. Okay. Yeah, thank you for clarifying. Yeah. Okay, so when we look at determining this geometric factor for wind, it's harder because we need to know how much is the roofline wind speed reduced when it gets to the house. We need to know how the pressures are distributed on the different walls with positive and negative, as well as the vertical distribution of these pressures and the internal pressure of the house and how it changes with wind. So how the infiltration models, specifically the LBL model, tries to get at it is it kind of makes this mystical mix of old wind tunnel studies, averages across walls, a bunch of assumptions, as well as downscaling for local shielding. It makes this C prime term and then it puts it into to this equation. And I believe, Paul, correct me if I'm wrong, I think during Dom's thesis defense, you mentioned that we know that all of these C prime terms are all extremely wrong, but no one's fixed them.
Yeah, that's correct. I mean, a house. So there's an analysis done of a bunch of data on test houses on the Alberta prairie, and the values that would have lined up with the measured data would have put shielding class 5, which when you read that description, very heavy shielding, large obstructions surrounding perimeter within 2 house heights. That's not the Alberta prairie.
Yeah, thank you. Yeah. So these C prime values are maybe not the most reliable, um, and but it's what is currently used in the model. So we have an opportunity to directly measure the pressures on the wall and to estimate flow from those direct measurements. We also can then compare those measurements to the flow estimates from the LBL model. And this feeds into to additional challenges. So we know that pressures are also affected by stack effects. So how can we determine only the wind effect and how the wind changes the flow? We also know that there's a lot of assumptions embedded into that K factor, the geometric factor, and some of those are invisible. So how do we test them to figure out what is reasonable and what is not? So with these direct pressure measurements, we can start to look at the total flow of the thing. And the total flow is great, but we want to know more. So our goal is to be able to take the total flow and to divide out the portions of it. So understand what is from stack, what is from wind, to kind of understand what are the influences from these different mechanisms on the home. Feeding this back into sapphires, this might be something where we might need to know, this would be useful to understand how big of a fan do we need, right? How big of pressure differences are we expecting inside and outside of the home? And how does the home behave in these different characteristics, right? If we have 90-degree days, is it even, or 90-mile-an-hour wind days, is it even worth it to try and build a fan to combat those differential pressures and that wind loading on the home? So to do that, and to try and achieve this goal of accurately attributing flow to specific mechanism, we are starting to look. That's why we instrumented 301 with so many manometers, and we are trying to calculate the flow at each segment of the wall using the differential pressure measurement at that segment of the wall. So kind of this little visualization on the right with this radioactive green from the official CSU color palette. We have 2 manometers on each side of each segment, and we divide the home into 3 sections. So there's the top, the middle, and the bottom. And Tammy and I have developed this equation to calculate the total flow. So Q total is the flow total. And basically what it does is it takes the leakage of each segment of the wall, and it divides it by the number of segments and the number of walls. It multiplies it by the differential pressure of that segment on that wall to the N, which is the leakage coefficient, so the quality of those holes. And then we sum it up to get the total for the entire house. And so
can I jump in here
Yeah.
just on that equation?
Mhm.
Because I'm guessing Paul's probably noticed we have no idea what's going on with the roof. Right. So we do want to portion some of the leakage to the roof. That's where the R comes in. And it's not in these equations, but we also have no idea what the pressure is across the roof. So right now we're just looking at the walls.
Yes. Yeah. Thank you, Tammy. So how can we use this to determine determine the wind contribution to flow? So from Dom's paper and from other work, we know that stack is well predicted. And with this method, we could potentially calculate the total flow into the home using these wall segments. So from that, we could back out 2 of these 3 terms. So we could back out Q total, we could back out Q stack. So the flow due to stack, the flow due to and the total flow as well, which from that, we could hypothetically get the amount of flow due to wind. So when we actually do this, when we actually plug the numbers into this equation, I haven't backed this out by different terms, and this might be the first time Tammy's seeing this, so everybody bear with me. So what we have here is gray is going to be wind speed, blue is going to be the total flow from the AIM model, green is from the LBL model and red is from this new one. So red is Q new. And very generally, you can kind of see that red is going to be lower than blue and green, especially when it's calm. But when it gets windy, red kind of increases. That Q new starts to approach the level of these other models. So let's dig into this. So we zoom into a couple different, I'm going to zoom into a couple different time periods. So this first one is August 3rd through August 6th. And we can kind of see what I just described. So kind of in these windy periods, like around here, after midnight on the 3rd, we see that Q new is pretty low compared to the AIM and the LBL are higher than the Q new. But when it gets windy, we see this red line Q new increases kind of into a similar amplitude to the LBL and the AIM model as well. There's even some interesting time periods. I think it's on my next slide. Yes. So there's even some interesting time periods where Q new will be higher than the AIM and the LBL. So kind of in this little period right here, and then in this period as well. So kind of maybe around 6 p.m. on April 3rd, 2025, we see that as well. Looking at a second time period, this is from the 8th to the 11th, and we can see that same pattern again. Tammy, I see a hand.
Sorry, no, I just want, can you go back to those? So yeah, folks, this is the first time I'm seeing these data. It's not like we weren't working on it. We were, it's just coming together. So work in progress, but Danny, those look mechanical, right?
Yeah.
And so I think what's happening is we're seeing the delta P in the real data affected by the mechanical, and probably can't be attributed to wind.
Mm-hmm.
And the LBL and AIM, of course, don't account for that.
Yeah.
Yeah, I hadn't picked up on that it looks mechanical, but you're right, it does. And I would be interested to know what the times are. I'm just looking at the scale. I'm guessing that is bathroom fan, showering, and then the range hood at dinner.
So I think the bath fans that we have are almost invisible in terms of pressure. So I think they all have to be range. The other possibility is the ventilation system that we have attached to the heat pump, which is
That's
similar
true.
to pressurization. You can see the pressure influence of that. But I think right now focusing on wind, it's not useful to try to compare what's going on with the mechanical. It's not that the mechanical is not of interest, but to try to figure out wind, I think we should just avoid those periods at first and then go back to them for explanation later.
Yeah, absolutely.
And Danny, before you move on, so what I'm seeing, so all three of these are a Q total, right?
Yes.
And so what we're saying then is that even when we are saying the flows are down around like 60 to 70, that just because of the wind, the other two models are basically doubling.
Yes.
I mean, that's what I'm seeing here is that if we're 60 or 70 at the beginning, they're up at like 125 to 140.
Mm-hmm.
And so that's how, and so we have some wind in there plus the stack, but your stack plus wind, their wind has a huge amount more. So I think the stacks are about the same across the three, aren't they?
I think they ought to be. I'm not sure why the stack is so, or why the baseline is so different. It's the thing I'm wondering about, because we think we're getting the stack right. So we'll have to think about that a little bit. But if you just look at the delta above the baseline, which is wind, then yeah, I think so one of the things we're working on is how to remove the stack effect fairly so that we can try to just look at the wind. And I think we may not be there yet, but I think we're close.
Yeah, and that's something that didn't quite square up when I was looking at these numbers, is that especially during these calm periods, it doesn't seem like um, it should be so much lower. Like it should be, half to a third as low, or of the QNU should be half to a third as much as LBL and AIM if we are calculating stack as it should. So that's something that I think warrants further investigation and to see what is going on in these numbers. Because when these things are when it's calm, they should hypothetically be similar, instead of them being more similar when it's windy.
I have an idea, but I don't want to go too far in the weeds with the audience that we have. But these are walls, right? The LBL and AIM are including the floor and the ceiling, and that's where the pressures are the
Mm.
highest. And so this part, what we should do is work with like a wall only estimate, which
Yeah.
we could pull out.
Absolutely. Yeah. Okay, awesome. So the second time period that I pulled out is April 8th through the 11th. And we see a very similar time period, or it's a very similar pattern to what we saw earlier in the month for this time period as well. So zooming in on this period with April 9th, this was something else kind of interesting in the data, was that instead of, if you recall, LBL and AIM were both much higher than QNU. In this case, QNU seems to track pretty well with the total flow from LBL for the windy period of time. So I thought that this was something interesting in the data. So it seems like the trend for QNU being different from LBL isn't always true, and that sometimes we can see some agreement between the models.
Well, that's just weird.
I know.
Because they've all got the same inputs, right? It's not like you changed the inputs.
Mm-hmm.
So curious.
Yeah. Okay, cool. So kind of starting to wrap up and opening this up for discussion. So some questions that we have are, is QNU a reasonable approach to mitigate the difficulties of using the K factor, of that geometric factor? And one thing I would like to know is, why is QNU consistently lower than the LBL and AIM during calm periods when LB and O are supposed to be well constrained during those times? And I think, Tammy, what you said about the floor and the ceiling, I think that could be a reason why we might be seeing these differences, as well as why does QNU track so well with the LBL during some windy periods? We haven't looked, or I haven't looked at extensively at the data record, so I don't know how prevalent these cases are. But if it happens more than once, I think that's something interesting that we could unpack a bit. Our main takeaways from this are that attributing pressure differences and flow to different mechanisms is still very difficult. And using different measurements of differential pressure presents an opportunity to calculate the flow for each wall segment. That's all I got. Any questions that anyone has about anything? Any thoughts, feedback?
Well, I have some thoughts, but I want to give other people a chance because I've talked more than anybody except you.
Can I give maybe a perspective on this work? So the tech that Christian and Paul are working on, Christian's taking input from a delta pressure sensor. So it's not necessarily using this information to decide how much flow to put in, which is good, because if they were waiting for us to figure out how buildings work, then we would never install anything anywhere. But this is sort of the building science part of it, trying to build that up so it can be a complement to just the simple empirical measurement.
I have a question or discussion point. First, super interesting stuff. I think I have lots of questions that I need to digest on, and I need to get into those equations a bit. But if we take a step back do you have a feel for how much these differences or discrepancies matter? And what I mean from that is like they're never going to exactly agree. They're never going to agree exactly with reality. We know that, we accept that. That's just the way numerical approaches work. But I don't have a good feel for the type of variation you were showing in terms of like real world impacts and how much it's going to matter, like in terms of an air quality standpoint or thermal budget standpoint, or have you gotten to that stage of do we care that they don't agree at the quantities you're seeing?
I don't know. I think I might pass this one to Tammy. Tammy, if you have any thoughts on answering that question.
Yeah, so I'm always happy to let you take it first, Danny, and then back you up. But so Christian, I think the overall principle here, which we haven't quantified yet, is that there's been a suspicion for a very long time that wind models overpredict probably by a factor of two. And so that means that if people are planning for windy periods, they're likely to overestimate the amount of flow that occurs and the amount of flow in your case that would have to be counteracted. And then it does have a, I don't, so let me just answer for the windy period. Yes, it does matter. It, because during those periods alone, wind is dominating the flow and it's overestimated. And likely the reason it's overestimated is some of what Danny showed, that people just made up shielding values and they don't seem to they were never really checked um, in in terms of the average. And so you can predict a large you can attribute a large amount to wind that doesn't actually exist. Um, so in terms of energy budget, you'd have to figure out how much those contributed over the whole year. And that's something that we're planning to do in Danny's paper. So it would be like we have not measured the whole year except for this one case, but we can extend it doing our best job by using weather data. And so first we look at the period that was measured and then we extrapolate to the whole year. So that's an answer we're probably going to have. Um, I think so. I think it matters for the general purpose that probably what we're trying to do is stick a fork in the current wind model and tell people to use something that's half as big. We don't have to get it right, right? But we do have to provide convincing evidence that that's what should be done. Does that
Yeah, that
answer
makes
some of your
sense.
questions?
It does, yeah. Hopefully it didn't come across as, well, why does this work matter? Because I do think it's important. I'm just trying to get a better feel, I think. And you started to answer this, so thank you for that from the standpoint of uh, we want perfection, but if we get within 20%, like that could be a huge win because it seems like we're
Mhm.
way off from 20%. We're
I'm never going to
200.
be looking for 20%. The wind is stochastic. We're
Yeah.
never going to be able to predict it. And I think one of the other things I want to do in Danny's paper is sort of exactly what you said. You're looking at time resolved flow data here, um, but then that uh, also buffers out when you look at the actual concentrations, right? Because the concentrations don't fluctuate that much
Hmm.
because the volume buffers that. And so a bias of a factor of two would lead to um, an overestimation of average ventilation, but not getting the fluctuations absolutely correct, I don't think matters at all.
Okay. Yeah, that's super helpful. Where my mind was going with some of those things is like we often get like a push from the standpoint of, well, how much would this be worth? Like from a dollar standpoint or a averted quantity. And so I was just trying to wrap my head around just because I don't know the space very well in terms of orders of magnitude there, but that was super helpful. Thank you.
Well, and then the other thing is what we've talked about with your with any air quality device is we might want to cover like 90 or 95% of the conditions. Well, if the wind is driving the tail, then it's also driving where your 90% cutoff is. So so it might affect the distribution of ventilation. And so you might actually have a lower um, maximum that you need to provide. And so then that affects the perceived or the estimated cost.
Yeah. I don't want to dominate here, so this is the last thing I'll say, and then I'll shut up for a while. Part of what I was thinking about was this going back with this was going back to that conversation we had last week about can you do more targeted interventions? And it seems like if there were going to be cases where we say, let's just throw more filtration at things or pressurization, like although we can't predict wind, something we can measure in like real time and ramp something up. So like from a large building standpoint, I don't think I've ever seen anything where ventilation or heating and cooling controls or any of those had any input from the wind side. But from what you're kind of showing here, it probably isn't large enough scale or impact, I guess, the way to put it, that having adaptive controls for windy versus not windy days could actually have some merit and benefits to it.
Yeah, that's something to think about. And yeah, we could go down a lot of rabbit holes here, but I will say that I think the answer for large commercial buildings may end up being different than for residential buildings that don't ever achieve a great height, and they're usually in a pretty shielded environment or frequently in a shielded environment. Other people that aren't Paul that might have questions about the meeting. Paul, I don't want to cut you out. I think you'll be able to fill the rest of the time once we give it to you. I'm just curious, are there like clarifying questions from people who are not so much in this field about like what does this mean or what are you doing or for explaining things that you think um everybody else knows but only you don't because probably everybody else then doesn't know.
Maybe I have a question. Maybe I just missed it though. Can you explain analytically what you're doing with this data? Are you doing like typical like regression? Are you doing time series? Are you doing machine learning? I guess I'm interested in the analytics part of it.
So we haven't done anything, any really analytical steps with it yet. Um, I think in terms of next steps that we will do, I'm not sure. Tammy, I think you have better perspective on this than I do.
So Erica, we haven't done any analysis other than comparing the measured conditions, what those measurements would predict in standard models that are used to determine ventilation rates and the ventilation that we would predict are using the slightly more um it not advanced but we have an intermediate measurement that isn't usually present. I have thought that it would be we have so much data that it would be very fun to do some kind of machine learning or machine learning is a random thing, but certainly there are um, like some kind of clustering for different kinds of conditions, I think would be really useful. Um, I've also thought following Christian's questions about does this matter, if we had archetypes of conditions that where weather conditions were correlated with dominant outdoor pollution, then there could be a more targeted discussion about when do you need to protect buildings and what are the typical conditions under which the buildings will be functioning when it's polluted. So I think there's lots of things like that. And right now, the equations that Danny showed are like, we apply those to every second. It's very simple because I think there's been a lot of the building science itself that's been sort of, I wouldn't say neglected, but people have assumed standard equations that were not tested. And so that's what we're exploring.
Yeah, no, that makes sense. So, and maybe Danny, this is for you. Assuming you could predict using like time series data, like what would be interesting to predict that would provide like practical value? Is there something that would be of interest? Like
Yeah,
if you
I
could
think
say in 5 minutes I can predict this is going to happen, like what would that be?
mm, I think in 5 minute increments,
Or
I would
any
love
increment. I was just making that up. Yeah.
no, I think 5 minutes is great because I think I would be very interested to know, in an ideal scenario, what the wind speed is at each level of the house. And so what is it at the top, the middle, and the bottom? And I think that would be very valuable to us to be able to look at how is it how is the wind loading across the face of the house. um, some of the very preliminary stuff that we've been looking at from 301 is that it doesn't seem like it's behaving how it should. And sometimes there's bigger pressure differences in the middle than at the top and the bottom, um, and during windy periods, which makes me think maybe there is something's a little off with the flow. So it'd be great to know, you know, again, an ideal scenario, what is it at the top, the middle, and the bottom, 5 minutes ahead of where it was. Yeah.
Okay. Yeah, that's interesting. Thanks. That helps me understand a little bit.
Yeah.
So I think one thing I'd like to, I don't know if I'd say predict, but one thing I might be interested in doing with machine learning or some kind of clustering algorithm is, as Christian's pointed out many times, these sensors, the pressure sensors are not very expensive. Are there places on the home, maybe hour 3 or maybe another 3, where you can put these diagnostic measurements and have it indicate the regime that the home is functioning under? And then have that be a plug-in to some kind of adaptive measurement. So I think we have to be careful about wanting to predict things. Like I've seen many, many, many papers where people want to predict the wind field around a house. And I think that, excuse me, is pretty much useless because it you have to do it for every house. And and you might be right or you might not be right. And I'm not sure it contributes to infiltration that much. But if you could have like a 3 sensor packet that would say, hey, you're mostly wind dominated right now, and that's 10% of the time, and so you better go into this regime. We might not have to predict exactly what's going on with the flow. We just have to know like kind of how to operate better.
Yeah, yeah, that makes sense. That's interesting.
So would you maybe ultimately, if you had, maybe, okay, would it be that you might say to a house, we're going to put the system in and you're in an area, the area around you has high wind is most important, so we're going to put you on that track. it's kind of like I'm thinking of like when you wash your clothes, and it's like, okay, generally you have this cycle you use or something because it fits most of the time. Would you be able to do something like that that would at least give more efficiency to that general kind of home's airflow, maybe?
Maybe something like that. Or Danny, jump in whenever you want. But okay, so I'm just spitballing here. Um, Unlike everybody else who had very precise questions. But yes, I think it's more likely that you would not ever have a house that was always in a windy condition. It would just be able to sense like, yeah, there's a pretty big wind event now. That means that if you try, I'll give an example using the pressurization system. If you try to meet the pressurization, you're probably going to fail. But by the way, it's windy. This isn't going to last very long. So maybe relax a little bit on the response time, or something like that.
Mm-hmm.
So teach it. Another example is I would, we haven't gotten into this yet, but I think we could sense when the windows were open, right? And so it's pretty dumb to try to run a pressurization system when the windows are open. And so it could it learn that like, oh, it behaves like this when, and I think Christian's got um some some algorithms too. And so it's not all about the pressures, but I think the pressures are pretty key input.
And
It's that,
I
I mean,
think
I think it's interesting from that, the perspective of, as a homeowner, how would it help me and what could it do that's better? And if the homeowner's asking, what if I open my windows? What is it going to keep running? I mean, if you've got some of that in there, that's pretty cool.
I think, Marilee, it would also be really interesting of if we could better understand kind of what happens to a house. Like, going back to those C prime, like, is it heavily shielded? Is it on a wide open Alberta prairie? Like, let's say there was someone on the wide open Alberta prairie that wanted to protect their home from smoke or outdoor air pollution, of communicating with them like, the fan must be 5 times bigger and it will be this much harder and this much more expensive to do the thing. If you want to take part in this, it's going to be, you're not the typical case. Or maybe you live somewhere like on the East Coast surrounded by, 100-foot tall trees, and your wind just, it never gets that much wind on the home. Then maybe you could scale down the fan or something similar like that. And so, like, figuring out which Legos go into the set to protect this, that go into the house.
Thanks. That makes a lot of sense.
So Tammy, your comment about perhaps we can get to a point where the system knows if a window is open. Where my mind went with that is I think a place that something like machine learning might be actually useful on a home by home basis is looking for changes in like the fingerprint of that home over time, which would be an indication of maintenance problems or damage or things like that, like a diagnostics of the characteristics of this home are different now than they were a year ago in a similar period. There's probably something wrong. You should go look for the leak or the crack or the break.
Yeah, and moisture, right? I don't know if
Yeah.
relative humidity, we have done nothing with it except use it to adjust the density so far. But it's probably not a terrible diagnostic either, as long as you have some information about the outdoors. Paul
So
probably had something to say about that.
I'll add real quick. I think I found a way to do it. Um, and I haven't validated it yet. And there's a little bit more work I need to do, but I think that there's a pretty easy way to take, I don't know if we can forecast it, but we can look at the variance in pressures and we can kind of subdivide them. But I haven't even talked to Tammy about this. I literally did this like 2 days ago. So once once we can dig a little deeper into it, then I think I'll bring it to the rest of the team. But if the initial data is right, it's pretty compelling. It's really interesting.
Okay, Paul, should we let you have a field day now?
There's only a couple minutes left, but and that's fine. I'm glad other people got to ask their questions. So let me just say, because I don't want us to have to go over, at least not by very much. I think this is all very, very interesting. I'm going to be gone through next week, but if there was, when I was in town, if there was an interest in getting together for kind of a data something meeting, hey, let's just brainstorm everything and look at stuff together. I would be really, really interested in participating in that. So a couple of things that have occurred to me. And I think there's a ton of really important applications for this. Some of them have been mentioned, but I think another thing, like let's say we were thinking about installing our equipment in a place like San Diego. San Diego tends to be pretty mild, and so stack effect may not be very big. And regardless of how big or small the wind effect is, when there's no stack effect, it's all wind. Everything you have is wind. And I think taking into consideration the fact that that happens sometimes is important. And with that, I think one of the things that I would love to see is, there's a couple of things I think could be looked at. One is when you see these differences between Q new and then the two models, is there a correlation between those differences and the indoor outdoor temperature difference? And is there anything any pattern with, say, wind direction? I'm wondering whether wind direction is what makes the green line sometimes be more close to the blue and sometimes more close to the red. It really could be wind direction that's doing that. And wind direction also could be contributing to, like, when it seems like the middle is more than the top or bottom. I think that's what you're saying happens sometimes. I also think, our house is not quite what the standard for the X and R is not quite what the X and R are thinking about. I mean, it seems maybe we're already excluding the floor and saying we only have 5 sides of leakage. We actually only have 3 sides of leakage.
That's what we're doing.
Okay.
Yeah.
But
Two-
I think
Two sides and the floor.
Okay. And so have you applied that same thinking for X and R to the LBL and AIM models as well?
Yeah, they all use.
Okay. And that was one of the things that I was wondering is, because I did something about 30 years ago. It was like if you assume a slab house instead of a basement or a crawl space house, it makes about a 20% difference in your predictions
Yeah, for
by having
slabs.
floor be zero.
Sorry. Go ahead.
Yeah, just by having floors be zero. So I was just wondering about that. But yeah, I think this is really, really interesting. I also think, the actual combination of stack and wind to get total isn't going to be linear. Like I would not expect, like when stack is zero, every CFM of wind is a CFM towards total. I would not assume that when they're being combined, when stack is not zero, that you get that for the same amount of wind, you get the same amount of additional CFM. So I think that's another thing is looking at maybe nonlinear models.
You want to address that, Danny?
I will let you address this one, Tammy.
Okay, I'll be quick because we're over. And then Danny, you can say if you disagree. So Paul, in general, for what the assumptions we're making for floor and ceiling, and this is not just this house, but all the ones that we did during Epic. If it has a slab, we're assuming no leakage. And then we're assuming the rest of the assumptions of the LBNL model, like there would be the same fraction in the ceiling. So we would just adjust the X and R in that way. If that makes sense. So then I can't
Yeah,
remember what so
I agree with that completely.
okay. And then the nonlinearity, I think, is something that Danny and I are looking at. I think the current thinking is we try to predict what the stack pressure would have been because we are confident in it at that point, and then attribute the additional pressure due to wind. So we have a counterfactual that's like, this would be what the stack would have done. And now here is the total, and then the attribution to wind is the difference.
Yeah, I agree with that. And I didn't mean to say that. I didn't intend to suggest that that was something I would disagree with. I think that's completely right. That is a contribution to infiltration from wind at that condition with that stack. But if as this process went forward, there may be some, and what does that increase look like for different wind pressures? And how does that change as you have different stack pressures, which could point you in the direction of an overall nonlinear model? But clearly, the difference between Q total and Q stack is the additional contribution from wind at that condition.
Yeah, well,
So
Danny mentioned that one of the things that's, I don't know if it's confusing, it's just like, oh dear. It is this the the standard view that appears in the ASHRAE handbook is this nice consistent wind pressure on one face, negative pressure on the downwind face. We know that doesn't happen. So there's a distribution of wind across the single face, which is supposed to be accounted for by the averaging in the wind tunnel studies. And so there's not just a lot in how they combine, it's also that the wind representation itself was always too simple.
that's a definitely a good point. Anyway, that's all I'm going to put forward now because we are over, and I think we'll have time to geek out about this more later.
Awesome.
I really like that, Danny. That was great.
Yeah, thank you. And I'm happy to send the slides out. But thank you everybody for listening. Thank you for the great questions. And Paul, we'll have our people get in touch with your people about talking about data.
Fantastic. That's awesome.
And if anyone would like to join that meeting, please just speak up and we'll make sure to loop you in about times. Thank you, everyone. Have a good weekend.
Bye, thanks.
Thanks, everyone. Bye.